Okay. So let's start our lecture today. So, sorry, I think there is a easier way to do this. So, yeah. So let's start. Let's just start the other way. So, um, so so here instead of defining the PC to be this one, right? So wait. Yeah, so we define PC to be this one, right? So instead of using the antiderivative, so because finally I figured out that after talking to some talking, so I think what I have is that yeah, after talking to my advisor, so I figured out that so here it is from 0 to z, right? So I think in general it is not true that so here, right? So for this definition of the PZ, right? So what we have is that we have like the start with over d square, and then we plus the sum over this omega not equal to 0 of 1 over this lattice point, right? So z minus omega square plus 1 over omega, like z over omega square. Sorry, 1 over omega square, I think. Wait, hold on. Hold on, 1 second. So, yeah, so it should be minus. Sorry, it should be minus. Yes. So, and then, so what we have is that, so this is PZ, right? Yeah, so let's, so, okay, so this is PZ. Okay, so it's the same definition. Okay, so it's the same definition. So, so yeah, so because this FZ basically you just take the limit of this partial sum, right? It's the same thing as just setting here, right? So it's just taking the negative FZ, which is the negative of this one, right? So which is this one, and then plus over the square. Yes, it's the same definition, but instead of using go from PC and do the antiderivative, because there is one issue with the antiderivative. So even though we show that, so here the logic is not kind of correct, because it's correct up to this line integral, right? Because the line integral is well defined for yeah, the line integral is well defined for this FZ and this SNZ. So this statement is in general true, right? So this statement is true, okay. So what is not true is that, so this is not true. So why this is not true? Because we cannot say the integral from 0 to z, because in our domain of definition, right? So there are these lattice point. So because so it is not true to write the notation 0 to z of fz, right? Sorry, f of zeta d zeta, because simply because because there are some, so there are singularities, right? So basically, there are singularities at the lattice point. So if there is a singularity at the lattice point, we cannot really define this for as a zeta, right? So if there is a singularity, then it is not true to define the integral from 0 to z to be just the path integral, because if there is a lattice point, then it is not path independent for the line integral, right? So because if there's no missing point, then we know that the line integral over like a closed one form, sorry, not closed one form, but a holomorphic function is always equal to 0. Yes. So and then yeah. So and then but if there's a missing point, then yeah, maybe I want to be more careful. Yeah, I think it's true. Yeah, I think it's true. So if yeah, this is true. So yeah, so but if there is a hole, right? So if there is a hole, then you may not get the path independent property, right? So if there's a hole, then this path may not be equal to that path. Yeah, so that is the issue about why we cannot use, in general, we cannot, this notion is not applicable in this case, unless this function, there's no pole for this function. And also no vanishing, right? Yeah, so, oh, no vanishing, there's no problem. But as long as there's no pole, we can do that. Yeah. So here, so what happened is that so here what we do is that because of this property, so what we do is that instead of taking the integrals, which takes a while to get over with, we can just start from the zeta z, because this is well defined, okay, without doing the integral stuff. We'll start with the zeta z, and then we take the derivative of this zeta z, right? Because remember that, so here, I just read this one. Because remember that this zeta z is a limit of holomorphic function, right? So on the domain C minus the wedge, right? So since this zeta z is the limit of a sequence of holomorphic function, oh sorry. So maybe I should say uniform limit, because I think yeah, so I will say what I said. Yeah, of holomorphic function Snz, right? So in this case, this Snz is not the same as this one. So maybe I should use another letter. Let's say S hat Nz. Okay. So where this S hat, and then so let this S hat Nz to be the partial sum. Because this function, we know that it has the uniform convergence, right? So sorry, the absolute convergence. So therefore, we can freely exchange any order. So Snz to be yeah. So we follow this order. Yeah. So we follow this order that defined in the previous scenario. So of the this guy. Okay, and then here what we have is that it's a uniform limit of a sequence of polynomial function S and Z on compact subset of C minus the wedge, right? So we have shown that in the past. So therefore zeta Z is holomorphic, right? And we have that the derivative of this S and Z, right? Prime Z will converge to the derivative of this limit, right? And then, and also locally uniformly, right? So LU means locally uniformly. So locally uniformly is like uniformly on compact subset. Okay. Locally uniformly, let's say on this C minus this wedge. Uniformly on compact subset. And then let's so this is the abbreviation for locally uniformly. So and now what is this S and Z? So since this what is this S prime Z? So since S sorry, what is this S n hat prime Z, right? So this S n hat Z prime is basically so we take the derivative of this guy. So what we get is that so this is negative 1 over Z minus omega n squared, right? So the summation n from 1 to infinity of negative 1 over Z minus omega n squared, and then this 1 over omega n is gone, and then the last one becomes plus 1 over omega n squared. Oh, sorry, this is the final sum, so it should be up to n. It's equal to that. And then we show that this limit, right? So therefore by this statement, right? So I think last time I'm using a double star to denote this statement here. So therefore by this double star, so we have that we have so since this S and Z prime by this argument converges locally uniformly on any so converges absolutely and uniformly on the constant subset of so this should be C minus wedge, right? Yeah, so it should be C minus wedge. But maybe I forgot to denote the C minus wedge. So so by this argument, so we have that Okay, sorry. So I think I missed one more step. So this zeta z is not really just the sums, right? So this zeta z is really okay. So let's get back to the y stress 0 criteria. So what is this zeta z really? So I think this zeta z is it should start with 1 over z, right? So it's not just the partial sums, well not just the sum term, right? So it is also the let's see what. Yes. So this zeta z is this one plus 1 over z. Okay. So I forgot I forgot one part, right? Okay, so okay, so I think there is no problems until wait. So how can I deal with 1 over z? So I think I can handle it by using zeta z minus 1 over z, right? So so I keep the S and Z the same definition. So what I have is that I have instead of converging the zeta prime Z, right? So this really converges to the derivative of. So I want to say is that it converges to the derivative of zeta z minus 1 over z, right? So ddz of zeta z minus 1 over z, right? So since it's zeta z minus 1 over z, okay, so let's do that. Minus 1 over z, right? If I take away this 1 over z, then this part, right, just by itself, it is the uniform limit of the sequence of holomorphic function as n z hat on compact subset of C minus wedge, right? So this is the same argument if we just replace all the zeta z by this zeta z minus 1 over z, right? So and then, so therefore this Sn prime z, right? So same argument, Just say that this Sn prime z converges locally uniformly on compact subset of C minus wedge. and then this ddz of, so locally uniformly on C minus wedge. So locally uniformly on C minus wedge means that uniformly on compact subset of C minus wedge. Yeah, and then, so this converted locally uniformly to this guy, right? So which is the same thing as, sorry, I will try to give you this one. So which is the same thing as zeta prime z, right? Wait. So this zeta z is what? Yeah, so what is this zeta z? So this zeta z is just the limit plus 1 over z, okay. So this zeta z is just this limit, right? So from here we show that this limit exists. So this limit plus 1 over z, okay. Yeah, so this is how we define zeta z, just the limit plus 1 over z, okay. And then this zeta z minus 1 over z, okay, yeah. So, and then, so therefore we have that, and then what we have is that, so by the double star we have yes. So by the double star we have what? Wait. It is not double star. Yeah, it is not double star. So, yeah, so we have oh yeah, it is double star because we use the double star to define this fz, right? Oh. Okay. Oh, sorry, this is equal to zeta prime z plus 1 over z squared. Right, because we take the derivative, yes. So, so the double star just tells us that, so this limit of this guy, right, which is the same thing as this one, is exactly our fz here that we use to define this pz, right? So we have that so let me just say this, and then we shall denote this limit function fz, okay. We have that, so this so therefore, because we know that, so this limit, which is the same thing as this limit, is our fz, right? So we have that this fz must be equal to the same because it's the same limit, right? The uniqueness of the limit is equal to that, right? So therefore, so this PZ, right, which is equal to negative FZ plus 1 over Z squared, is equal to zeta prime Z. Oh, sorry. Negative zeta prime Z, right? Because this is negative FZ. And then minus 1 over Z squared plus 1 over Z squared, which is equal to negative zeta prime Z. So therefore we're done. Okay. Alright, so this set us the well-definedness of this PZ and zeta Z together with relation that this the derivative of this state, this PZ is just the derivative of negative zeta prime, sorry, the derivative of zeta Z. Sorry, this PZ is just the negative zeta prime Z. Okay. Alright, so yeah, so next time we'll just continue to show the periodicity of this zeta Z. Okay. Periodicity of zeta Z. Okay, so see you next time.